Okay, go right into it. So this is the chemistry paper 2 class for tomorrow's chemistry exam, sorry. So what I'll do is just like the last classes, I'll be going through all the exam questions that I've got together and I'll be going over content. And the chat is open as well. If you've got any questions, drop them in as we're going, or you can ask at the end as well. So let's jump right into it. You still need to remember your chemistry paper 1 knowledge as well, like some of them, not as in depth, but you should be aware of like certain bonding, um, certain ways that reactions happen and such. So you still need to know your ionic equations and such as well. So just make sure you don't forget your paper 1 knowledge. And there is the paper 1 video on YouTube as well if you do want to go over that after this class. For this exam, you need to know the test for 4 different gases. So for hydrogen, it's the squeaky pop test. So you get a lit splint, you put it inside a test tube, and it'll make a pop sound if there is hydrogen. You've got oxygen, which will relight a glowing splint. So say you've got a splint, you've taken out the fire, you put it back into the test tube that's got the oxygen, it'll relight again. The carbon dioxide test is the lime water test, and if carbon dioxide is present, the lime water will turn cloudy. And then chlorine, that bleaches litmus paper, turning it white. So make sure you know it for them 4 gases. Let's have a look at this question. So it says, give 2 reasons why the percentage of carbon dioxide in the air has decreased in the last 2.7 billion years. So just before answering this question, you need to know about the early atmosphere and you need to know about the atmosphere as it is today. So let's just quickly go over that now. So the atmosphere right now, inside the air, which is known as a mixture, is mostly nitrogen. So we can say roughly 80% of the air is nitrogen. And the reason why most of it is nitrogen is because billions of years ago, the early atmosphere, I'll just call it early atmosphere, also had a lot of nitrogen as well. And this is due to volcanoes. So because that nitrogen hasn't gone anywhere, the nitrogen is still lingering from that time. So that's where the nitrogen has come from. It's unreactive. It doesn't really do anything, and it's still in the atmosphere today. What else is in our atmosphere? We've got oxygen, which is roughly around, you can say 19 or 20%, but it's roughly around that figure. And back in the early atmosphere, there was barely any oxygen. And the reason why there wasn't any oxygen was because there was no life form. So there was nothing respiring. So no plants, no animals for respiration and photosynthesis. So there was no oxygen in the air. And every other gas, so stuff like carbon dioxide, water vapor, sulfur dioxide, these all make less than 1% of the atmosphere as it is now. But in the early atmosphere, there was a lot of more carbon dioxide than there is now. Again, that's due to the volcanoes. Another thing that was also present in the air in the early atmosphere was also water vapor. But so in today's atmosphere, it's now less than 1%. So again, the reason why there was a lot of water vapor was because of the volcanoes. So it's a common exam question for them to ask, well, why has carbon dioxide and water decreased over time and now it's less than 1%? Well, the carbon dioxide, that's what this question's asking here. Give 2 reasons why the percentage of carbon dioxide in the air has decreased. So the first reason is photosynthesis. So plants came about and the plants use the carbon dioxide for photosynthesis. So remember, photosynthesis is carbon dioxide plus water, which we give to the plant, makes glucose plus oxygen. I'm just going to change that to the word format. So this photosynthesis, as you can see, it uses carbon dioxide. So therefore, the carbon dioxide in the air decreased from the early atmosphere, and now it's less than 1% in the air. And this photosynthesis also explains why oxygen has increased. So as you can see, photosynthesis produces oxygen, and that's why there was a rise in oxygen in the atmosphere compared to the early atmosphere. Okay, what's the second reason that the percentage of carbon dioxide in the air decreased in the last 2.7 billion years? It's also because they were dissolved in oceans. So this water vapor, it was quite high in the early atmosphere. It decreased because oceans then formed that water vapor that was gas, changed to liquid, became the oceans, and it also trapped a lot of the carbon dioxide within them oceans as well. So they're the 2 answers. Make sure you're aware of the composition of the atmosphere today and how it was in the early atmosphere as well. Okay, so I've put some notes here. This is just everything that I've discussed. So volcanoes being the reason of increased carbon dioxide, nitrogen, and water vapor, dissolved in oceans, and so on. Plants and algae, photosynthesis, and then oxygen gradually increase. So this is everything that I've just described above. Okay, moving on. It says, what is a symbol for a reversible reaction? So you should know that a reversible reaction is just represented like so. So it basically means that reactants can go forward to produce products, but products can also go backwards to produce reactants. So that's the symbol for a reversible reaction. It says complete the sentence. In a reversible reaction, the forward reaction is exothermic. So that means it gives out heat. So the reverse reaction is endothermic. So remember, with reversible reactions, if one way is endo, the other way would be exothermic. So it's just always opposite of each other. Same goes for if one way was cooling. So let me just rub that out. So if, say, the forward reaction happened if I cooled the reactants, then the backward reaction would happen if I heated the product. So it's always the opposite of each other. Okay. Moving on, a reversible reaction happens in apparatus which stops the escape of reactants and products. Complete the sentence. Equilibrium is reached when the forward and the reverse reactions happen at the same rate. So remember, rate of reaction is how much either products is being formed per time or how much reactants is being used per time. So just be aware, rate is something that they test quite a lot in chemistry paper 2. It just means either the amount of products made per time or it's the reactants used per time. So it's always per time, so usually second. Can you say speed? Equilibrium is reached on the forward and reverse reactions happen at exactly the same speed. I would say speed is correct, but the mark scheme would want that particular word rate just because rate of reactions is that first topic in chemistry. So I guess you could say speed, they might accept it, even though you are correct, but I probably would use the word rate instead. Okay, that's cool. So just like all your other science exams, you still need to know about your variables for this. So make sure you know the difference between independent, dependent, and control. Control variables are the ones you keep the same. You don't want it affecting your investigation. Independent is what you're changing, and then dependent is what you're measuring because of that. A really common question in the exam is they ask, how can you improve an investigation? All you would say is take more measurements. So I don't know, the investigation could be how metals react in water, for example. Rather than just taking 4 measurements, you could take maybe 10. So your investigation would therefore be improved because you'd have a better mean. So that's usually what they expect in the mark scheme. Okay, combustion. What is combustion? Combustion is what happens in our cars. So we put fuel into the car. It reacts with the oxygen that's in the air, and then that forms carbon dioxide and water. And the whole purpose of combustion is for energy. The reason why we burn fuel in the car is because we want the car to move. So that's the whole point of it, to release energy. Remember, we can't create energy, but we release energy. So that's the whole purpose of combustion. But there's 2 kinds of combustion that can happen. So there's complete combustion and there's incomplete combustion. What complete combustion is when it happens with enough oxygen. So if there's enough oxygen, the fuel will react with oxygen and it'll form carbon dioxide and water. However, if there's not enough oxygen, then incomplete combustion is going to happen. And what's going to happen here is carbon monoxide is going to form instead of carbon dioxide. Now, carbon dioxide is quite bad because it is a greenhouse gas. So it contributes to global warming. However, carbon monoxide is a lot worse. It's a gas which you can't smell, you can't see it, and it causes breathing problems and can essentially kill someone. So this is more dangerous if carbon monoxide was formed. And just remember, the chemical formula for carbon monoxide is CO. So mono means 1, so you can see 1 oxygen. Carbon dioxide is CO2, so di means 2 oxygens. Keep that in mind. I have seen in past papers where sometimes for incomplete combustion, instead of carbon monoxide being formed, sometimes just carbon is formed. So just remember, incomplete combustion, it does not form carbon dioxide. Either produces just carbon or it produces carbon monoxide. So this is the what wants to happen, essentially. Okay, so that's incomplete combustion. You might be asked to give an actual example with it. Does carbon monoxide contribute to global warming? No. For GCSEs, you don't say that. You say carbon monoxide is dangerous to animals and humans. It's because it can kill. In terms of global warming, it's really carbon dioxide and methane that you want to talk about. Okay, so yeah, sometimes you can be asked, well, what fuel could that be? That fuel, the most common example they give is ethane. This is both foundation and higher, Liber. So if there is something higher, I will say that it's higher. So a common fuel they use is ethane. And you should know the chemical formula for ethane. It's 2 carbons, so C2. And then H, there's 6 of them. So I'm going to go on to naming alkanes and alkenes just in a minute, and you'll see why it's C2H6. But yeah, make sure you remember them 2 versions of combustion. Okay. Okay, catalytic cracking and steam cracking. What's the purpose of these? So cracking, what is cracking? Cracking is when we get a really long chain hydrocarbon. So say something like, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's just say something like this. So cracking is where we basically break down these really long hydrocarbons into shorter hydrocarbons. So we could break it. We could break it here. We could break it here. It doesn't really matter. But what you need to remember from cracking, the 2 things that are formed are an alkane and an alkene. So it's a common exam question for them to say, okay, cracking's happened. What will form? As long as I would recommend drawing out the carbons and hydrogens. Just crack it and make sure you've got the number of hydrogens and carbons right in your products. So I'll show an example of that. But anyways, that is what cracking is. You form an alkane and alkene. And the reason why you do this is because you want more useful products. So longer chain hydrocarbons aren't really that useful. You could use it for bitumen for the roads, but you can't really use it as fuel or LPG, or you can't use it for jet fuel and so on. So we crack them to make it more useful. Okay, so how do we do cracking? So there's 2 ways we can crack: catalytic cracking or steam cracking. So catalytic cracking, it's in the name. This is with a catalyst, and you have to remember the name. So it's a zeolite catalyst. A zeolite is just a type of metal. And it happens at 550 degrees Celsius. So make sure you remember that number as well. Steam cracking, there's no catalyst. It just uses steam. But you need a higher temperature, so temperatures of more than 800 degrees Celsius. So you can imagine this process of steam cracking is a lot more expensive. So you might get a 4 marker just saying evaluate both versions of cracking. You would say steam cracking is a lot more expensive because you need higher temperatures to crack the long chain hydrocarbons. But the catalytic cracking, this zeolite catalyst is quite expensive as well. So but then again, it's useful for the long run because you're using low temperatures. The zeolite catalyst is what's dropping this 800 down to 550. So make sure you remember the catalyst names and you remember the temperatures as well. Okay, moving on. Actually, one other thing as well. If they ask what are alkenes useful for, they're useful for polymers. So remember, polymers are just types of plastic, but don't use the word plastic, use the word polymers. So that's what they're useful for. Okay, so you need to be able to name certain alkanes and alkenes. So let's go through them. The starting word is meth, eth, prop, and bute. So the way I remember it is monkeys eat peanut butter, but you might have another acronym to remember it. So how do we use this? Well, anything with this, so methane is just 1 carbon, and carbon is in group 4. So I'll just show you here. Carbon's in group 4. So that means carbon can have 4 bonds. So just remember each carbon that you have must have 4 lines to it. So remember alkanes and alkenes are types of hydrocarbons. If they ask you what is a hydrocarbon, it's a molecule consisting of just hydrogen and carbon. That's it. So this needs 4 bonds, and then 4 bonds are going to be hydrogen. So we can see methane is CH4. Let's do ethane. So ethane is 2 carbons this time. This carbon here has already got 1 bond to carbon, so it needs 3 more bonds. And this carbon on the right-hand side, it's got 1 bond already, it needs 3 more. 1, 2, 3. So you can count C2, 2 carbons, and 1, 2, 3, 4, 5, 6 hydrogens. Okay, so remember in the combustion example, we said ethane is a really common example, so you can see that C2H6. Okay, we've got propane. So propane is 3 carbons, so C3. 1, 2, 3. This one needs 3 more bonds. 1, 2, 3. This carbon here already has 2 bonds, so it needs 2 more. And this carbon here already has 1 bond, so it needs 3 more bonds. We can put in the hydrogens. You don't have to put in the hydrogens, by the way. If you just draw them as sticks, you'll still get the mark as well. Just in case it's a really long hydrocarbon, you don't have time to do it. Okay, so H6, 7, 8. And then finally, butane is 4 carbons. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C4H10. So you should notice a pattern with these alkanes. It's CN, H2N plus 2. So that's the formula for actually doing the molecule. So for example, ethane has 2 carbons, so C2, and then 2 times 2 is 4, add 2 is 6, so C2H6. That's where it comes from. So you might need to use this maybe to give the molecule of a really big hydrocarbon like C20. Then you would know that it's C20, H 20 times 2 is 40, 40 add 2 is 42. So that would be the alkane with 20 carbons. So that's why you need to keep the molecular formula in mind. Okay, so that's how you name the first 4. So you've got methane, ethane, propane, butane. They might ask you for 5, 6, 7, and 8 as well, but it just follows the normal shape convention. So after butane, the one with 5 carbons is pentane, like a pentagon has 5 sides. After pentane, it's hexane. A hexagon has 6 sides. After that is heptane, like a heptagon. Octane, like an octagon, and so on. They don't really ask for that, but just keep it in mind as well. Okay, let's do the alkenes now. Now, what's the difference between alkanes and alkenes? Alkanes just have single bonds, whereas alkenes have double bonds. So there's no such thing as methane, because if I had a carbon, where am I going to stick? I need a double bond with another carbon. So there's no such thing as methane. So it starts from ethene. So ethene. So notice the ending is -ene, and for alkanes it's -ane. So for ethene, it's got 2 carbons. However, because it's an alkene, it's got a double bond. So I'm going to put a line here. Now remember, each carbon has 4 bonds. So this carbon here already has 2 bonds. It needs 2 more. And this carbon here already has 2 bonds. It needs 2 more. So just remember, every carbon has 4 lines drawn off it. You shouldn't be doing any more than that. Okay, so we can see the formula is C2H4. Let's do propene. So it's 1, 2, 3 carbons. But remember, you don't draw your double bonds on both of them. You just choose one and you just put 1 line. So I'm going to put it there, but it doesn't matter which one you choose. Now, this carbon here has 2 bonds, so it needs 2 more. This one in the middle has 3 bonds, 1, 2, 3, so it only needs 1 more. And this one at the end has 1 bond, so it needs 3 more. So that's propene, C3H6. And then finally, butene, 4 carbons. It doesn't matter where you draw your double bond, just choose a place. I'm going to choose there. This carbon here only has 1 bond, 1, 2, 3. This one has 3, so just 1 more. This has 3, so just 1 more. And then this one has 1, so it needs 3 more. So that's C4H8. And this time you should notice that for the hydrogens, it's just doubling the carbons. So you can see here, 2 carbons, so 4 hydrogens. It's 3 carbons, so 6 is double of 3. Same with butene, 4 carbons, so it just doubles to give you 8. So the formula for alkenes is CnH2n this time, so it's just double the number of carbons. So be quite aware of how to name and draw each of your alkanes and alkenes. So they're pretty good marks. Okay, we've already covered complete and incomplete combustion above. Don't know why I put it in again. We've already covered that. Okay, we've got a question here. Ethene is an alkene, which you should be, when you're reading these questions, keep in mind what it looks like. So you know ethene is C2H4. Give a test for alkenes. Now, and give the result of the test if an alkene is present. So basically a positive test. Now the test for alkenes is the bromine water test. So in addition to the 4 gases that I told you above, so for hydrogen, oxygen, carbon dioxide, and chlorine, you need to know these tests, but you also need to know the test for alkenes. There is one pure water test that you need to know about as well, which I'll come on to as well. So it's the bromine water test. And what happens is the bromine water is orange. And if there is an alkene present, it's going to turn colorless. So just make sure you write as words. You would just say the bromine water starts off with an orange color, and if there's an alkene present, it turns colorless. So that's the test for alkenes. This is not for alkanes, by the way, just alkenes. Okay, what is conservation of mass? It's a bit like conservation of energy in physics. Conservation of mass basically says your mass of reactants equals the mass of your products. So whatever you put into a reaction has to come out of that reaction. So say, for example, on this side, if I had 10 grams of reactants I've put in, then I need 10 grams of products coming out. But sometimes in real life, that doesn't really happen. So you might get asked the question, well, how come sometimes your products weigh less than your reactants that you put in? And what you would say is the 2 points you would put for that is that one of the products will be a gas. Hopefully they should give you an equation and there'll be like a G on one of the products. And what you would say is the product has dissipated. So dissipated means it's gone away. Dissipated as a gas. And your second mark would come from saying because a closed system is not used. So if you're doing a reaction and you're not using a closed system, then if you're forming gases, then gases will escape. So that's the reason why sometimes your products do not weigh the same as your reactants, but conservation of mass is still true. It's just the fact that you've not captured all that information. Okay, let's continue. It says copper sulfate is produced during the extraction of copper from the Earth's crust. Copper is produced from copper sulfate solution using iron. And here's a word reaction. So whatever they've just said here is just explaining what's happening here. It says from the equation, a company calculated that 648 kg of copper sulfate, so copper sulfate 648 kg is needed to produce 617 kg of iron sulfate. So I'm just labeling this on the diagram. And 258 kg of copper. Calculate the mass of iron. So mass of iron is this one, needed to make 258 kg of copper. So just using the rule that we just spoke about, conservation of mass, whatever you put into the reactants has to come out on the products. So if I calculate the products where I've got 617 plus 258. So if I just work that out, 617 add 258 is 875 kg. So that's the products I've got. So that means my reactants together, these two together, must be 875 kg. I know the copper sulfate is 648, so to work out the iron, all I need to do is 875 minus 648. And that gives me 227 kg. So this is just a conservation of mass question. Okay, pretty easy marks. Okay, so these are from paper 1. You should recognize these reaction profiles. They don't usually write potential energy for you guys, they just write energy, but it's the same thing anyway. I'm just going to cross out. Okay. So what this is showing is an exothermic and an endothermic reaction. And as you can see, let's start off with the exothermic reaction. This is the reactants and that's the products. So you should notice the products is lower than the reactants. It's because the reactants have lost energy, as in an exothermic reaction, you're giving out heat. And this hump here is known as the activation energy. What is the activation energy? Now, for a reaction to happen, so I'm just going to write here, reactants go to products. For a reaction to happen, them reactants have to collide with enough energy for the products to be formed. If they just touched slightly, the reaction wouldn't happen. So it has to have enough energy to actually become products. And that energy it needs is called the activation energy. So the definition is the minimum amount of energy needed to start off a reaction. So as you can see with this exothermic reaction, I need this much energy, so that's the activation energy. I need this much energy for the reaction to happen. If I didn't have that much energy, the reaction won't happen. So your activation energy, you work it out from the bottom of the reactants to the top of the peak. So let's have a look at this endothermic one. So there's the reactants, there's the products. So remember, reactants are always slower. You can see this endothermic reaction needs a lot more higher activation energy. So starting from here to the top, it needs more activation energy because endothermic reactions take in heat. You're giving in heat, so therefore more energy. So how can we lower this activation energy? Well, we can add a catalyst. So I'm going to do this in a different color. If you add a catalyst, so remember a catalyst is something which speeds up a reaction, but it doesn't get used up. So an analogy you can think about, if you're making a cup of tea, you put sugar into that tea, you don't just leave the sugar there for it to dissolve. You get a spoon, a metal spoon, and you mix the sugar. So your spoon is acting as a catalyst to dissolve that sugar a lot faster, but the spoon, you can use it again. So just like a catalyst, speeds up a reaction, but you can use it again and again and again. Now, what a catalyst does is it lowers the activation energy. So looking at that peak, you can see the activation energy now is lower, so it changes the reaction pathway. So same with an endothermic reaction, as you can see, it's going to lower the activation energy. So I'll keep that in red there. What else do you need to know? They might ask you what's a catalyst known for in biology. It's enzymes. So remember, enzymes are biological catalysts. They tend to sneak that in, even though it is biology. So enzymes are just biological catalysts. They speed up a reaction and they do not get used up. Okay, so that's a little bit about reaction profiles. It is in paper 1, but they do bring it in paper 2 as well because it relates to rates. Let's continue. Okay, so potable water. What this basically just means is water that is safe to drink. It's written there actually. So water that is safe to drink is potable water. So it needs to have low levels of dissolved salts and microbes. We don't want microbes in there because causing disease. So tap water basically is potable water in the UK because we can drink it. It contains dissolved substances, so they might add different ions into it to be able to kill certain bacteria, for example. And it comes from fresh water in the UK. So fresh water in the UK is stored in reservoirs. So reservoirs has fresh water in, and that fresh water is changed to potable water. Now, what fresh water has inside is stuff like microbes. It has like twigs and branches and mud that all needs to be cleaned out before it becomes potable water. So we use sterilizing agents such as chlorine, ozone, ultraviolet light to actually kill the microbes. If supplies of fresh water are limited, so what this basically means is like hot countries. So take Dubai, for example, they're not going to have reservoirs to be able to store water in because it's mostly hot there. So the reservoirs would always keep evaporating. It wouldn't be able to contain the water. So areas where there are no fresh water, they have to use the ocean water. But the issue with the ocean water is there's very high amount of salt. So you have to remove that salt, and that's a really expensive process, and that's known as desalination. So desalination can be done by distillation or using membranes such as reverse osmosis. So the disadvantages is it requires a large amount of energy. So if it requires a large amount of energy, it's a really expensive process. So that's where if in Dubai and places like really hot countries, they need to get it, they get it from the oceans, but it's quite expensive to do so. Okay, so that's potable water. And so yeah, I would say just make sure you know the difference between potable water and fresh water. Fresh water is not drinking water. Okay, so let's move on to this question. So this question has come up in a few past papers. I've not really seen it in the content, but it does come up in past papers. So it says describe a test for pure water. Now, pure water is something that contains nothing added inside it. It's just pure water. So it says give the result of the test if the water is pure. What the mark scheme says is that you need to boil the water. So that's the test that you're carrying out. And the result from that test is that it will boil at 100 degrees Celsius. Because if it boils at 100 degrees Celsius, that's the boiling point of pure water. So therefore, it is pure water in that case. So that's the test if the water is pure. So hopefully that does come up tomorrow, and that's a nice, easy 2 marks. Okay, moving on. This question is about atmospheric pollutants from fuels. So I've put a table here for the atmospheric pollutants that you need to know about. So we've spoken about carbon monoxide, how it can essentially kill, and the reason why it's bad is because you can't see it, you can't smell it. So that's the reason why we have carbon monoxide alarms for that reason. We've got sulfur dioxide. So I'll just write the chemicals here as well. So sulfur dioxide, SO2. This is acid rain, essentially. So sulfur dioxide contributes to causing acid rain, which corrodes metals and erodes stone. So when you look at certain statues, you might have discoloration on top of the statues. It's because acid rain has gone onto them, but it also causes breathing problems as well. So that's sulfur dioxide. Nitrogen oxides, they sometimes call them the NOx gases. You don't really need to know the formula of what it is, but just know that it contains nitrogen and oxygen. I have seen a past exam question where they say that cars can produce dangerous nitrogen oxides, and they say, how does it form this? Well, what happens is in the atmosphere, there's nitrogen and oxygen. And what the car does is because the car is really hot, it heats these and it changes them to nitrogen oxides, which then is an atmospheric pollutant. So that's how cars contribute to forming nitrogen oxides. And then we've got soot, which is just carbon particulate, so it's just carbon. And this can cause health issue and it can cause global dimming. Now, carbon, it's like loads of little dust particles essentially. And if there's a lot of dust forming in the air, that's going to block light from coming in. So therefore, it seems a lot darker. So that's what global dimming is, less light reaching the Earth because you've just got all these carbon particles, this soot inside the atmosphere. Okay, so be aware of them for atmospheric pollutants. This question says, fuel burns in a car engine. Describe how oxides of nitrogen are produced in a car engine. So it's just what we discussed, actually. So what you say is, your first mark comes from saying there's a high temperature from the car engine. Now, remember, we have a high temperature from the car engine because the whole point of the car is to do combustion so your car can move, essentially. So that's the reason why we've got a high temperature from the car that's already there. And what happens is this enables the oxygen and nitrogen from the air to react. and then in turn, oxides of nitrogen are produced. Okay, that's cool. Let's move on. Okay, so we've got a calculation question here. Most of the calculation questions they do ask you in paper 2 is just common GCSE maths questions. It's nothing like how paper 1 is with all them different calculations, but they can bring them over. You might end up seeing moles, for example, in tomorrow's exam. So just make sure you don't forget what a mole is for higher students, not foundation. But yeah, just don't forget them calculations from the first paper. So it says here, a sample of river water contains 125 milligrams per decimeter cubed of dissolved solids. Okay, I can already see there's going to be probably an issue with the units because we don't really work with milligrams and decimeters cubed. It says calculate the mass of dissolved solids in grams. So we want to change it to grams, so milligrams to grams, in 250 centimeters cubed of this sample of river water. So this is just a proportions question. So we've got 125 milligrams in 1 decimeter cubed. How much have we got in grams in 250 centimeters cubed? It's a 4-mark question, just testing you on proportions and give you answer to 2 significant figures. So remember, centimeters cubed to decimeters cubed, we divide by 1,000. Let me do it this way, actually. We divide by 1,000. So remember, decimeter cubed to centimeters cubed, we times by 1,000. And then milligrams to grams. Let me get rid of the arrow there. So milligrams to grams, we divide by 1,000. And then grams to milligrams, we times by 1,000. So don't forget these unit conversions. Okay, so the questions told us a sample of river water contains 125 milligrams per decimeter cubed. So basically in 1 decimeter cubed. That's what per decimeter cubed means. Now, what I need to do is I need to change this 125 milligrams to grams. There's a few different ways you could do this, actually. You could do your final answer and then change it right at the end. You could change the decimeter cubed to centimeter cubed. It doesn't really matter as long as all the units are the same. And at the end, you give your answer in grams is basically what matters. Let's change that 125 milligrams to grams. So we're going to be dividing by 1,000. I'm just going to write 125 over 1,000 grams, and that equals 1 decimeter cubed. That decimeter cubed I can change to centimeters cubed. Decimeter cubed to centimeters cubed, I'm timesing by 1,000. So 125, let me actually work that out. 125 divided by 1,000 is 0.0125. No, 0.125, sorry. Okay, and then we're doing 1 times 1,000 because we're changing it to centimeters cubed. So 1 times 1,000 is just 1,000 centimeters cubed. Okay, perfect. So we've actually got both of them now. I should be writing the units. I've got them both to grams and centimeters cubed now. So I've done the hard part, changing the units. The question wants you to work out 250 centimeters cubed. So how much grams is in 250 centimeters cubed? Now, how do I get from 1,000 to 250? Instead of doing that, I could first go 2 seconds. Again, there's a few different ways you can do this. You don't have to do this way. I could find 1 centimeters cubed first. So I divide by 1,000. I'm going to divide that side by 1,000. Proportions, whatever you do to one side, do to the other side. At this point here, I just did my unit conversions. Now, this part here was the proportions. Just keep that in mind. Okay, so I'm going to do 0.125 divided by 1,000 grams. Now, to get from 1 centimeters cubed to 250, I'm timesing by 250. So I'm going to times this by 250. And the answer I get is 0.125 divided by 1,000 times 250. I get 0.03125 grams. But the question says give your answer to 2 significant figures. So I've worked out how much grams in 250 centimeters cubed. I need to change that to 2 significant figures. So I'm looking at that 2, and that keeps the 1 as is. So my answer is 0.031 grams. That's a nice 4 marker. Which of the unit conversions do we need to know for tomorrow's exams? The centimeters cubed to decimeter cubed and milligram to grams is really important. I would say anything with a kilo, make sure you know that's with 1,000. And just your standard maths ones as well. So I would say, like, make sure you know in a meter there's 100 centimeters, because you don't know what they're going to ask, but they can ask you anything from GCSE maths. But in terms of chemistry, I would say these 2 are the main ones, and anything involving kilo. So for example, 1,000 grams is in 1 kilogram. So yeah, just remember them. Okay, moving on. Formulation. So what's a formulation? It's a mixture that's been designed to be a useful product. So you have to say the word useful product. You can't just say formulation's a mixture, because you have to say that mixture is useful. So an example of a formulation could be fuels, cleaning agents, paints, medicines, alloys, fertilizers, foods. You're mixing things to make useful things. So that's a formulation. Make sure you know chromatography. This might be the practical that comes up tomorrow, because they've not tested it in paper 1, I believe. So there's a high chance that chromatography could come up tomorrow. So let's go over it. So the whole point of chromatography is you're using it to separate out mixtures, and you're basically identifying what's in that mixture. So just looking at this, the way you do it is you'll have a solvent. That solvent is usually water. You've got filter paper. You draw a pencil line on that, so make sure it is a pencil line, because if it was a normal ink line, that will spread as well. Pencil line won't spread. And then you dip in the filter paper, but you make sure your filter paper isn't fully dipped, like the line is above the water, as you can see. You don't want to dip in your actual solution in. And as you can see, you put your sample that you're testing, what's in, onto the paper, and then as you dip it and you leave it for time, it'll start separating out, and it'll separate out into what's in that mixture. And then you can work out RF values, you can compare it to non-RF values, and work out what's in there. So this could easily come up as a 6 marker tomorrow, as like just explaining the method. The 2 most important things to write is about mobile phase and stationary phase. So remember, stationary means still. So that's the way I remember it. Stationary means still, and your stationary phase is the filter paper. The filter paper is your stationary phase. Your mobile phase, which is moving, is the solvent. So it could be the water. So this water, the solvent that's moving up, that's the mobile phase. So make sure you describe the mobile phase and the stationary phase in your chromatography question. Okay, the RF factor. So what you do is, the way you do it is the distance the substance has moved. So say, for example, we're working out of this green dot here, the RF value. You measure it. So let's say that's 2 centimeters. And you divide that by the distance the whole water has traveled. So let's say the water traveled right to there, and that's 5 centimeters. We would do 2 divided by 5, and we would work out our RF value that way. They might give you a table and they'll say identify what it is. You just match the number to what the number is in the RF table. Okay, so yeah, it's a mixture separating out into pure substances. So you don't want to lose marks on chromatography, so definitely keep that in mind. Okay, so chemistry plays an important role in sustainable development. What is sustainable development? So remember, sustainability is basically what are we doing today that's not going to affect future generations to come, for example. So that's the reason why they want us to use electric cars, because electric cars are more sustainable than petrol cars, because it's not using fuel. So it's more sustainable. So the 2 marks comes from saying it meets the needs of current generation. So as in us. So let's say the sustainable development I'm talking about is an electric car. So it's meeting the needs of our current generation, so us, by the fact that we can still drive a car. And the second mark comes from saying without compromising needs of future generations. So meaning that us using electric cars is more sustainable than using a petrol car because fuel is a finite resource. Crude oil will eventually run out. So that's what it means by sustainability. Okay. This question is about hydrocarbons and crude oil. So remember crude oil, let me just show you on the summary sheet what is crude oil. Okay, so crude oil is a mixture of loads of different hydrocarbons. So you wouldn't call crude oil a formulation, by the way, because it's not useful as is. We separate out. And the way we separate out is using fractional distillation. So we put the crude oil into the fractioning column. Right at the bottom, we add a lot of heat, so it's more hot on the bottom and it's more cooler towards the top. The shorter chain hydrocarbons will move towards the top and then get tapped off, and the longer ones stay at the bottom. So I would just say, remember certain examples from each of this fractioning column. So the LPG, petrol on the top, the bitumen on the bottoms. So that's the fractioning column. It says hydrocarbon fuels are produced from crude oil. Describe how crude oil is separated into fractions for 4 marks. So basically describe what's happening in that fractioning column. Okay, so where do the 4 marks come from? The first mark, either you'll say heat or vaporize crude oil. So that's your first mark because we're putting the crude oil in, there's a lot of heat on the bottom, and that's essentially heating the crude oil, or you can say the word vaporize because we are changing it to a gas to be able to rise up the column. That's your first mark. Your second mark is saying there's a temperature gradient in the column because it's cooler towards the top of the column. Right at the bottom, it's more hot. Towards the middle, it's in between. So it's changing. There's a temperature gradient in the column. So you would say the vapor, i.e. the gas, condenses into fractions because when it's rising, so we're talking about hydrocarbon fuels are produced from crude oil. Describe how crude oil is separated into fractions. The vapors condense is going up as a gas, and then as it's coming out of the tap, it's then condensing, and then that's how it gets tapped off. So the vapor condenses into fractions, which is all them levels. And then your 4th mark comes from saying, where does exactly this vapor condense? So you would just say, depending on the boiling point. Because at different levels, they'll have different boiling points. The shorter ones more towards the top, the longer ones towards the bottom. So that's where your 4 marks come from. Again, you don't have to write it as bullet points. You can just write it as a paragraph, but you have to hit each of them 4 points. Okay, balancing equations. I would always recommend leaving balancing equations last completely. If you see a balancing equations question, just come back to it. It'll be 1 mark, it'll be 2 mark, but it tends to sometimes take time and there's no point. So the way I would recommend doing them is, first of all, the ones that are by itself. So I can see oxygen is by itself here. I'm going to balance oxygen last because that's the easiest. List what atoms you've got on each side. So I've got carbon, hydrogen, and oxygen on both sides. So carbon, I've got 4, so that little number. I've got 10 oxygens on the left-hand side. Remember, the left-hand side is everything to the left of the arrow. And I've got 2 oxygens. And on the right-hand side, I've got 1 carbon, I've got 2 hydrogens, and I've got 2 oxygens. Okay, so when we're balancing equations, we can't change the little number. We put a number in the front. If you're asked why do you balance equations, it's because of conservation of mass. Whatever you put in has to come out exactly the same amount on both sides. So let's deal with the carbon first. I've got 4 on the left-hand side, but I've got 1 on the right-hand side. I'm going to put a 4 in front of the carbon, which changes this to 4. But now my oxygens have changed because this 4 affects the oxygen. So I've got 4 plus 1, so I've got 5 oxygens now. Okay, let's deal with the hydrogens. I've got 10 on the left-hand side, I've got 2 on the right-hand side. So I need to make it 10, so I'm going to put a 5 in front of here because 5 times 2 is 10. But now I've affected the oxygens again. So I've got 4 oxygens and 5 oxygens. 4 add 5 is 9. Okay. So my carbons and hydrogens are balanced for both. Now I just need to sort the oxygen out. So I've got 9 on the right-hand side, but I've got 2 on the left-hand side. So to change this 2 to a 9, what do I times 2 by to get 9? It's 4.5. So 4.5. Or you can write 4.5. And 4.5 times 2 gives me 9. So you can leave your answer like that, but if you don't like the decimals, you can just double everything up, but you'll still get the marks. So remember, there's a little 1 here. If there's nothing, it's not 0, it's 1. So if I double everything, just so I can get rid of that 0.5, I can double this 1 to a 2. I can double the 4.5 to a 9. I can double the 4 to an 8 and the 5 to a 10. And that's my answer. So you can leave it as a decimal version or you can leave it as whole numbers if you just double everything up. But again, I would recommend leaving balancing equations completely last. Okay, this might come up tomorrow as well. A lot of kids don't really like this topic. So this is talking about the short and long wavelengths, which essentially are contributing to global warming. So as you can see, I'll just describe this diagram first. We've got the sun and we've got the earth. The sun emits, I'm just going to write this on top because you can't really see it. Short wavelength radiation comes from the sun. So as in the UV radiation, the UV rays, they're all really short wavelength radiation, which you should know from physics for paper 2 on Monday. So that's what's coming into the earth. Now, what then gets emitted back out is long wavelength radiation. I'm just going to write long here. But this grey thing that's here surrounding the earth, they're all the greenhouse gases. So they're the greenhouse gases. So stuff like carbon dioxide, methane, that's essentially created a barrier. So you can see this long wavelength radiation, instead of just passing straight out, is bouncing back into the earth, and in turn that's causing global warming and climate change. Okay, so what question have we got? It says here carbon dioxide is a greenhouse gas. Describe the greenhouse effect in terms of interaction of short and long wavelength radiation with matter for 4 marks. So this is exactly what I've just described, but let me show you how they write it in the mark scheme. They want you to say that short wavelength radiation enters the atmosphere. So just what we described, so the short wavelength comes from the atmosphere from the sun. So if you want, you can say UV from the sun. You won't lose marks for saying it, but it's still part of that same 1 mark. So that's your first mark, talking about short wavelength radiation coming into the atmosphere from the sun. Our second mark is saying that it's absorbed by materials and re-emitted. So the sun that's coming in, it's getting absorbed by essentially certain things, and it's going to emit back out, so as long wavelength radiation. So this re-emitted, when it's re-emitted out, it's long wavelength radiation, so these red arrows here. So that's where your third mark comes from, saying as long wavelength radiation. And then finally, what you need to say is the greenhouse gases, don't allow it to just go through, it's going to bounce back in to the earth, which is going to cause the greenhouse effect. So let's write that down. You say it is trapped by a greenhouse gas, which they've told you in the question, carbon dioxide, which stops radiation escaping. So therefore, the temperature is going to increase. So that's your 4 marks. So if you get this question tomorrow, just keep this diagram in mind. And remember, it's the short ones that are coming from the sun, and then they get emitted as long wavelengths, but they don't come out because the greenhouse gases are re-emitting them back in. So there are your 4 marks. That increases temperature, which then causes the greenhouse effect, which basically is global warming, climate change. Okay, so this isn't a question I'm necessarily going to answer, but I just want to speak about it. Just because of time, there's no point plotting. Now, what this question said was, here are temperatures and the time that these temperatures happen in the context of whatever question it was. The question basically said, plot the points and draw a line of best fit. So 2 marks, basically. So as you can see, they've plotted the points and they've drawn a line of best fit. So notice how they've not just joined all their points together. They've just drawn one straight line from the top to the bottom, approximately going through the middle of all them points. And as you can see, it's a negative correlation. So yeah, if you do get that question tomorrow to plot a line of best fit, please don't just join all your points together. Draw a line of best fit, which is just one straight line, and use a ruler as well for that. They're easy marks, you don't want to be losing. Okay, so for the last part, for anyone that is doing foundation, you don't need to know any of the next part that I'm going to talk about. So if you do want to drop off now, hopefully that was helpful. The recording to this will go up as well, but everything I'm talking about here on is just for higher. So yeah, and good luck with the exam tomorrow for any foundation students. But I'll continue on with this. Okay, so just for higher tier only, you need to know about Le Chatelier's principle. Now, where Le Chatelier's principle comes into is reversible reactions. So reactants going to products and products basically going backwards to reactants. Now, let's say this is a really common process, the Haber process, and this is the formation of ammonia, which farmers use as fertilizer, and they create it from nitrogen and hydrogen. Now, a farmer would want to make sure there's more products formed. They don't want the reaction to go backwards. They want to keep it going forwards. So they can use Le Chatelier's principle to figure out what should I do with temperature, pressure, and concentration to keep this reaction going forward. So that's what we're going to discuss. And remember, these are just for reversible reactions. So Le Chatelier's principle says if a system at equilibrium is subjected to a change, remember that change can be temperature, pressure, concentration, then the system will adjust to counteract that change. Okay, so for temperature, if you increase the temperature, that's going to favor the endothermic reaction. So you just need to remember that. If you increase the temperature, that's going to favor the endothermic reaction. So if I decrease the temperature, what do you think that'll favor? That'll favor the exothermic reaction. So it's just the opposite. Oops, 2 seconds. Exothermic reaction. So I've got a question on this. I'm sure I do. Nope, not that one. Okay, so this one here. So this one's a good question. It says the equation for this reaction is this, and it says this reaction is at equilibrium, meaning we're going to use Le Chatelier's principle. It says the reaction is exothermic, so it's saying the forward reaction is exothermic. So even though it doesn't say forward reaction, when it says the reaction is exothermic, they're referring to going in the forward way. So that's exothermic, so backwards is endo. Remember, it's opposite. The question says, what happens to the equilibrium position when temperature has been increased? Well, we just said, if you increase the temperature, that's going to favor the endothermic reaction. And in this example, the endothermic reaction is backwards, which is to the left. So you would just say shifts towards the left-hand side. Okay, so that's for temperature. Let's have a look at pressure. Now, with pressure, this is to do with the moles in front of the reaction. So if we look at this reaction, we can see there's 1 mole of nitrogen because there's 1 in front of it. There's 3 moles of hydrogen and there's 2 moles of ammonia. So we're just reading the numbers in front of the equation that they'll give you. So if you increase the pressure, this is going to favor the reaction that produces fewer moles. So in this case, you can see on the left-hand side, let me do it in red. I've got 1 plus 4 moles. So I've got 4 moles on the left-hand side. And on the right-hand side, I've got 2 moles. So if I'm increasing the pressure, that's going to favor the reaction with fewer moles, and fewer moles is forward. The products has less moles. So if I increase the pressure, more product is going to be formed. So increasing pressure shifts equilibrium to the right. Okay, so that's increasing pressure. You always look at the numbers in front of whatever you're producing. Okay, concentration. Increasing the concentration of reactants, meaning more product is formed, which makes sense. If I put in more nitrogen into this reaction and more hydrogen, then that means there's more nitrogen and hydrogen to react, so therefore it'll go forward. So that's what concentration means. If I okay, let's have a look at this one. This is a concentration question. So it says here, the reaction between oxygen and sulfur dioxide is at equilibrium. Some of the sulfur trioxide, which is this, is removed. So we've removed some of the sulfur trioxide. So what's going to happen to the position of the equilibrium for 2 marks? So what you would say is, thinking about the concentration above, we would say the equilibrium shifts to the right-hand side. And the reason why it's going forward is because you've removed some of this SO3. So if you've removed it, then there's less of that. So then there's reactants to react to make more product. So it's going opposite this. We've said increase in concentration of reactants, more product is formed. But if we decrease the concentration of the products, that's still going to shift it to the right-hand side as well, because you've got more reactants. So you need to think about, what have you got more of? So therefore, what's it going to react? Which way is it going to react? So equilibrium shifts to the right-hand side, and you give a reason. You say because concentration of SO3, so sulfur trioxide, decreases because you've just removed it. Okay, so that's Le Chatelier's principle in terms of temperature, pressure, and concentration. So pressure, you look at moles. Temperature, you look at if it's exo or endothermic. And concentration, look at if you're increasing the reactants or you're increasing the products or decreasing each of them. Okay, so that's Le Chatelier's principle. Something from rates of a reaction as well. So figure 4 shows the results from a different investigation. Okay, irrelevant. So you can see volume of gas and time. So this is a rate equation because it's how much volume of gas is getting released as time is going on. It says here, determine the rate of reaction at 20 seconds for 5 marks. I'm not going to finish this question, but I'm going to tell you how you do this question because it is pretty easy, 5 marks. So the rate of reaction at 20 seconds. So the way you work out the rate of reaction from one of these graphs is, because it's a curved, I can't work out the gradient of a curve. To work out the rate, we're basically finding the gradient of something, because remember the gradient, right here, the gradient is what's on the y-axis divided by the change in the x-axis. And on the y, we've got the volume of gas produced, so basically products produced, divided by the time. And products divided by time is rate. So how can we work out the gradient of this curve at 20 seconds? Well, you don't work out of the curve. What you need to do is you need to get a ruler, find 20 seconds, which is here, and you're going to draw a straight line. So we're going to draw a tangent. You get a mark for drawing this. So you draw a tangent, and you're working out the gradient of this tangent. So it's up to you how you want to work out that gradient. You can use whatever you've learned in maths. So you could do the triangle method, then do your change in y divided by your change in x. Or you can find 2 points on here. So let's say that point and that point, and you do the change in y divided by the change in x of your coordinates, and then give your answer to 3 significant figures. Should be self-explanatory. So they're really nice, easy 5 markers. So you don't want to lose marks here as well. Sometimes they might say give the units of the rate. Well, we can see it's centimeters cubed divided by seconds And that's the same as saying centimeters cubed per second. And that per, you can change that to centimeters cubed s to the -1. They'll accept that as well, because 1 over s is s-1. So there's a bit of higher level maths, which is why it's higher. But it's not too bad for 5 marks. Okay, so this is the final part. Okay, so for higher, you need to know about 2 methods of extracting copper, and that's phytomining and bioleaching. Now, what phytomining is, you basically grow plants in an area where you think there are certain ores of copper there, but low-grade ores. You plant loads of plants there, the plants will grow, and the copper ions from the ground will basically grow inside that plant. You then harvest the plants, you burn the plants, and in the ash, you collect the copper ions from there. So that's phytomining. Bioleaching is with a bacteria, and you need to know the bacteria name, the solution it produces, sorry. So you say bacteria produces these solutions which contain copper ions, and then they be extracted. So you basically get bacteria into that area, and they basically eat away at the copper, and then you get it from them. These methods have smaller impact on damaging the environment because you're just using plants, you're using bacteria, compared to traditional methods. So remember from paper 1, your traditional methods are stuff like electrolysis or stuff like reduction with carbon, really expensive to do. So that's an advantage of it, but the disadvantage is that they're slow and produce very low yields. So what yield means is basically not enough copper to make it worth it. So that's the reason why you don't really see these methods take place, because it produces low yields. So let's have a look at this last exam question. It says this question's about copper and fuels. Copper is extracted from low-grade ores by phytomining. So remember, there's phytomining and bioleaching. It says describe how copper metal is produced by phytomining for 4 marks. This is how you get the 4 marks. So the first mark, you say you grow plants on a low-grade ore, just as we said. Your second marks comes from saying you burn the plants. So plants are burnt to produce ash. Now our final marks are how we exactly taking the copper out of that ash. So the third mark is saying the ash is dissolved in acid to produce a solution of a copper compound, because there'll be other things mixed in that ash that you don't want. So that's why they put the ash in the acid, so they get a solution of copper compound. Now we need a way to get the copper compound out of that solution. And you should know from paper 1, we can use electrolysis to of the solution to basically extract the copper. On the mark scheme, they will also accept displacement instead of electrolysis. If you do say displacement, you can also say that, but that's your paper 1 knowledge tested here as well. But anyways, I think I've covered majority of chemistry paper 2 there. I haven't talked too much about what increases the rate of reaction, but it's pretty self-explanatory. If you increase temperature, that'll increase the rate of reaction. If you add a catalyst, that'll also increase the rate because you need lower amount of energy. If you increase the surface area, that also increases the rate because you're making it smaller, basically. You can kind of think of the alveoli from biology, a bit similar to them. If you increase the concentration of reactants, so you put more reactants in, of course, you're going to make more products. And if you increase the pressure, you're going to allow for more collisions to happen. What topic should we go over chemistry paper 1 for paper 2? It's a good question. What I would say is you just, we've got a chemistry video which kind of covers majority of the basics. So this video will get uploaded to here as well, this session that's just happened. But there is a chemistry paper 1 class, which is roughly an hour. So I'd recommend watching that to get a rough run through of all of chemistry paper 1 as well. But other than that, I think I have covered the majority of chemistry paper 2. So any questions on that? I hope you did find that helpful. And I'll get this uploaded as soon as possible as well, so you can go back over the session if there's certain sections you want to go over again. But hopefully everything I've covered does come up in tomorrow's exam. No worries. I hope that was helpful. And good luck with tomorrow. Can you send the questions out? Can you complete the 5 mark on the rate of reaction? Yeah, I'll do that now. I'll do that now in that case, just before I send it out. But hopefully tomorrow's a good exam and you get quite a lot of marks to increase your grade overall as well.